So this video is on the topic of differential equations. I'm just going to do a really brief introduction to them. There's actually a whole class devoted to differential equations, so this is just kind of the initial look. We'll just touch on them briefly in this class, and then if you're, hopefully it'll pique your interest and you want to study it more, and you can take the class later. So a differential equation is an equation that has derivatives in it. So, and here's the example I'm going to use is a very practical one, and this might shed some light into something that you have known all your life, and it'll give you some insight into how, well, not all your life, but since pre-cal at least, how it will show you how one of the functions, or one of the equation formulas that you use quite often, how it was derived. So, so we're going to start with this little fact that if a rock is falling through the air, the acceleration caused by gravity is -32 feet per second squared. So this of course doesn't look like a differential equation until we stop for a moment and think about that acceleration is the derivative of velocity with respect to time. So we could rewrite this equation as the derivative of velocity with respect to time is -32 feet per second squared. Okay. So now it's a differential equation. It's an equation with a derivative in it. Now let me provide a little bit more information. Let's say that we know that when at time 0, so we know something about the velocity function. At time 0, the velocity of the object was 10 feet per second. And we also know that the height of the object, it was dropped off of or was thrown off of a cliff. So the height of the object at time 0 was 100 feet above the valley that it's dropping to. Okay? So we're going to use this information to come up with a formula for the height of a formula that can tell us the height of the rock at any time based on the time since it left the person's hand. Okay, so here's my differential equation. It has a derivative. The derivative of velocity with respect to time is -32 feet per second squared. So the way we handle, one way to handle differential equations is this technique called the separation of variables. So we're going to ignore the units for a minute and just deal with the equation itself. So notice that there's a v here and a t there. V stands for velocity, t stands for time, right? So we're going to multiply both sides by dt, and so we'll end up with dv, oh, that's a horrible d, dv is equal to -32 dt. Okay? So so then notice that we have v on this side and t on that side. So now what we're going to do, because we're trying to get back to velocity, is we're going to integrate, because we know that acceleration is the derivative of velocity. So if we want to get a velocity equation, we'd have to integrate, because we're going backwards, right? We're undoing the derivative. So I'm going to integrate both sides of this equation. And if I integrate, of course the integral of dv is just v. And the integral of -32 dt would be -32 t. Now remember, because we don't have any limits of integration, we have to include a plus c here, because if -32t works, -32t plus 5 also works, or plus 10 or 7 or whatever, okay? So this is a velocity equation. It's a general velocity equation, but we happen to know something specific about the velocity equation. We know that when you plug in 0 for t, you get out 10 feet per second. So what we're going to do is we're going to take this little equation here, and we're going to say we know that v of 0 is equal to 10. So that means 10 has to be equal to -32 times 0 plus c. So that means that 10 has to be equal to c. So now I'm going to rewrite my velocity equation and say that this is velocity equals -32t plus c, because I just found out that c was 10. Okay. Now remember, our goal is to come up with an equation that will tell me the height of the object based on the time since it left the person's hand. So I have a new equation here. It's a velocity equation. And since I'm looking for height, I realize that actually, just like acceleration was the derivative of velocity, we know that velocity could be thought of as the as the derivative of height. Because if you take the change in height over a change in time, that would be how fast it's falling. So that's the velocity equation. So I'm going to rewrite this as dh dt equals negative 32t plus 10. And so then I realize I have a differential equation again. So I'm going to separate variables again, and I get dh is equal to negative 32t plus 10 times dt, because I multiply both sides by dt. Now it's set up nicely so I can integrate both sides. So I take the integral of both sides, and I get h on this side, and over here I get, well, it's got to be t squared, and if I multiply out front by 2 and drop the power 1, I would get 2 out front, so that means we need a negative 16 in here to make it work out rightly. And of course the integral of 10 would be 10t, and then we needed a plus c again. And so now we have a height equation with this little general thing over here, so we got to adjust that. So we know up here this information that h of 0 is equal to 100. So if I plug 0 into this equation down here, I get negative 16 times 0 squared plus 10 times 0 plus c, which means that 100 is equal to c. So now I can rewrite this equation. So my new formula is h of t equals negative 16t squared plus 10t plus 100. And many of you, if you've taken physics or if you paid attention in Pre-Cal 1, you've seen this formula before. This is a formula that we use for anytime something in the air, something is in the air and falling. And remember that that right there is your initial velocity, and that right there is your initial height. Well, now you know where that formula comes from. We use differential equations. We solved a series of differential equations to get that formula. Okay, so that's the introduction to differential equations and why they're so helpful. Let me just do a couple more examples, ones that are not connected to a context. Let's say that we just have in general a differential equation that's dy dt is equal to, we should do dy dx. dy dx is equal to xy, for example. So here's another equation, and sometimes there are differential equations we can have the independent and dependent variable mixed, but we can still do the same thing. So when we do the separation of variables, I got to get the y over here with dy and the dx over here with the x. So I'm going to divide both sides by y, so I get dy over y. I'm going to multiply both sides by dx, so I get x dx. And so now I'm going to integrate both sides, just like I did before up there. The integral of dy over y, well, that's just natural log, right? So that would be natural log of y. And the integral of x would be 1/2 x squared. And then we need a plus c. Now, I'm going to stop here for a moment because those of you that have been paying attention might be wondering, I integrated both sides, so why didn't I have a c on both sides? That's a great question. I'm glad you asked that. If we did have a c on both sides, let's go over here for a second. That would have given us natural log of y plus c is equal to 1/2 x squared plus c. But they'd be different c's, like c1 and c2, let's say, right? And remember, c is just any numerical constant, right? So if I have a constant over here and a constant over there, I could subtract c1 from both sides, and I'd have natural log of y is equal to 1/2 x squared plus c2 minus c1. And of course, c2 minus c1 is just a constant also. So I could rewrite this as natural log of y is equal to 1/2 x squared plus some other constant, and we'll call it c sub 3. So the point is that I don't have to put a c in both places because they can just be compounded into one by adding them together. So that's why I only do a c in one side. Okay? So generally when we solve a differential equation, the first one I did, notice that it was explicit, so we had the independent variable by itself as the derivative and everything else on the other side. In this case, after I integrate, I'm not left with the dependent variable by itself. So my next move is to get the dependent variable by itself. So now remember from pre-cal, the way you undo natural log is exponentiate both sides, which means we're going to make both sides of the equation a exponent of e. So we get e to the natural log of y is equal to e to the 1/2 x squared plus c. And of course e to the natural log of y undo each other, and we get just y. And over here, remember when you're raising something, when you have a exponents add together, this can be rewritten as e to the 1/2 x squared times e to the c, because remember, x a times x to the b is equal to the x to the a plus b. So what we're doing is taking this and going back to that. And e to the c is just another constant, right? It's a number. So we can rewrite this as y equals k times e to the 1/2 x squared. And then that would be my solution. Now, what do we mean by solution? That means that if you take this function and plug it in for y up in the original equation, it makes that equation true. So let's investigate that. We had dy dx is equal to, what was it? xy, right? So what we're suggesting is that this, if we take the derivative of that, if we plug y in every place you see a y here, you're going to make this a true equation. So first of all, what is the derivative of y? Well, the derivative of y is going to be, it's going to be k times e to the 1/2 x squared, and then the chain rule will kick out the derivative of 1/2 x squared, which would just be x. And if we leave x as x and replace y with k e to the 1/2 x squared, notice we get an equation that's true. So that's what we mean when we solve a differential equation. Just like when we solve an equation, we're looking for a number that makes the equation true. When we solve a differential equation, we're looking for a function that makes the differential equation true. Okay? So there's just a couple examples of differential equations. There is a sheet in the module where it has a bunch of differential equations that you can use. You can practice this. So have fun.